Okay, we're going to go through the reactions that comprise glycolysis. We've got 10 reactions here, and they start with glucose, right? So glucose we think of as a ring in the blood. It's cyclic, and it has 6 carbons with alcohol groups all over it. You need to be able to draw out either the alpha or the beta form of glucose, doesn't matter. Okay, so the first reaction is a kinase reaction, right? Kinases are a family of enzyme that use ATP to add phosphates to things. And so hexokinase acts upon glucose and uses ATP to turn glucose into glucose 6-phosphate. Now I'm not going to write out all the phosphates, I just put a P with a circle on them, right? And this reaction costs us an ATP. So when we think about accounting, how much energy are we using, how much energy is getting paid back through this process of glycolysis, we got to keep that in mind. Okay, so what's the molecule that's formed? It's glucose 6-phosphate, right? The phosphate's on the 6th position up there. The next enzyme that acts is phosphoglucose isomerase, which converts our glucose molecule to a fructose base. And we saw earlier that fructose is a 5-membered ring. Other than that, it's the same, carbons with alcohol groups all over it. And so we go from glucose 6-phosphate to fructose 6-phosphate. We haven't added any phosphates, doesn't cost us anything. We've just done an isomerization reaction here. Okay, missing an E. Fructose 6-phosphate. Okay, the next reaction is an incredibly important reaction, the most important reaction in glycolysis, because it is the rate-limiting step of the 10 reactions that we're talking about. And it is catalyzed by the most important enzyme, phosphofructokinase. Okay, phosphofructokinase is a kinase that works on this phosphofructose molecule, and so it also uses ATP, and it puts a second phosphate in the number 1 position of the fructose molecule. Oh, no, just an O and a P there to give us fructose 1,6-bis phosphate. Now again, since this is the rate limiting step, maybe I should put a little highlight around this. This enzyme is really highly regulated in glycolysis. If you want glycolysis to speed up, then you can activate phosphofructokinase. If you want glycolysis to slow down, you can inhibit it. Again, since it's the rate limiting step, the rate of glycolysis depends on the action of that enzyme. And so there's lots of molecules that will activate it and inhibit it. Most of these make sense, right? If you have a lot of ADP, then you probably need to make more through glycolysis. So ADP is an activator of phosphofructokinase. If you have a bunch of ATP, you probably don't need to make more, and so ATP feeds back and inhibits phosphofructokinase. And so we'll talk in class about that idea of feedback inhibition and logical molecules that might activate or inhibit different steps in the linear pathway. Okay, very important step. Okay, so once we have fructose 1,6-bisphosphate, this is where the lysis comes into play. We are going to cleave our 6-carbon sugar into 2 3-carbon pieces. And so let's put the 3-carbon pieces up here, right? One of them is a ketone. The other one is an aldehyde, right? Now, the ketone is called dihydroxyacetone phosphate, right? It's an acetone or ketone-based molecule. The other molecule is called GAP for glyceraldehyde, right? We got an aldehyde, 3-phosphate. Okay, and this is the cleavage step that occurs in glycolysis. Now, how many steps have we done? 1, 2, 3, 4. We've only got one more step in the first half of glycolysis, the energy investment phase. And this step's pretty simple. We're going to convert one of these DHAP molecules to a second molecule of GAP, right? And this is conducted by triose phosphate isomerase. And so we've got another isomerization reaction, just like we did up here as we went from glucose to fructose. Okay, so the net result of the first half of glycolysis is that we've used 2 ATPs, right? We've broken our 6-carbon glucose piece into 2 molecules of GAP. And so from now on, we're going to have 2 molecules of GAP per glucose going through reactions 6 through 10. Okay, reaction 6 is a really important reaction. It is catalyzed by an enzyme called GAP dehydrogenase. We're going to see a bunch of dehydrogenases in the Krebs cycle. I'm just going to label those DHs from the future, or in the future. And GAP dehydrogenase works on each molecule of GAP. It phosphorylates the molecule of GAP, but without using ATP. And the other thing it does is it converts NAD plus to NADH. Now, NADH, we said earlier, is a reduced cofactor. It's holding electrons, and we're going to harvest those electrons later in order to gain energy if we have oxygen. But this is also part of this oxidation reduction that's happening here. GAP gets acted upon by this enzyme to form 1,3-bisphosphoglycerate. So let's do, is this where I have my double bond? Yeah. Okay. So not only are we adding a phosphate to our aldehyde here, but we're turning it into a glycerate, right? More of a carboxylic acid functional group. Bisphosphoglycerate. And so we're taking an aldehyde, turning it into a carboxylic acid. That's part of the oxidative process of glycolysis. And since we're oxidizing this carbon chain, we're able to reduce NAD plus to NADH. Really, you can think of this H here as a hydride, right? A couple of electrons that are being held by NAD and NADH. We've reduced NAD to NADH, oxidized the glyceraldehyde to the glycerate through the action of GAP dehydrogenase. Okay. The next step that occurs is a kinase reaction. So phosphoglycerate kinase. And since we've seen kinases before, in this instance, we're going to be generating an ATP. And we have to keep the accounting in mind here, right? We have 2 gaps to make 2 of these molecules to make 2 ATPs. So I'm going to remind ourselves of that by putting a 2 over here. And really, we're getting rid of the phosphate on the first carbon. So let me draw out this molecule. And we end up with 3 phospho. I shouldn't have written that out. Glycerate. Okay. So we're starting to get energy back here. Really, we've already accounted for the 2 that we've spent. Now we've got those 2 back. So any more ATPs that we make in this process are going to be net profit, right, from the breakdown of glucose. Okay, next reaction, 3-phosphoglycerate goes to 2-phosphoglycerate. And, we could draw that pretty easy. And this is an interesting reaction. We're not just plucking off this phosphate from the 3rd position and sticking it on the 2nd position. Really, there's an intermediate that's formed in this reaction, which is called 2,3-bisphosphoglycerate, or 2,3-B, or DPG. The enzyme, well, I haven't told you the enzyme, the phosphoglycerate mutase. This mutase, just like the mutase we saw in glycolysis, is just switching the position of a phosphate group. The intermediate here is one that's got 2 phosphates on it. So really the enzyme puts a phosphate on the 2nd position and then plucks one off the 3rd position. Doesn't use the same phosphate and just move it. And this is an interesting intermediate because this is one way in which oxygen binding connects to glycolysis. It turns out that this molecule inhibits hemoglobin binding to oxygen. And so if you have an actively metabolizing cell that's burning a lot of glucose, it needs oxygen in order to support that metabolism. And so if a cell is actively burning glucose or going through glycolysis, there'll be a buildup of this intermediate 2,3-BPG. And so when oxygenated hemoglobin comes around this needy cell, it will encounter these high levels of 2,3-BPG, and this molecule will inhibit hemoglobin binding to oxygen. So hemoglobin will unload its oxygen on these needy cells and go back and get some more. So it's a way for a cell that's actively burning glucose to communicate to hemoglobin, give me your oxygen. In fact, I'm going to cause you to release it by the formation of this intermediate. Okay, we're almost done here, right? We've got 2-phosphoglycerate, which turns into a molecule of phosphoenol pyruvate. So we're almost at pyruvate. Okay, and we are losing a water as part of this reaction. Let me see, H2O. 1, 2, 3. I don't want to have too many oxygens here. Okay, pretty much we've formed an enol, this alcohol group with the ene. We've lost water, 1, 2, or H, another H here, and O to form a double bond here. And this is, catalyzed by the enzyme enolase. And then its PEP, this is also known as PEP, goes on to form our final product, pyruvate. And a pyruvate doesn't have, a phosphate group. So we harvest this last phosphate group to generate more ATP. And again, this is net profit ATP right here. And this is catalyzed by the enzyme pyruvate kinase. Okay. So if we think about the accounting, we've used 1 ATP, 2 ATPs. We've generated 2 gaps, which make 2 NADHs, 2 ATPs, and 2 ATPs here. So our net production of energy and potential energy is 2 ATPs and 2 NADHs.